Alright, we're going to start off with this question where we have a particle being placed outside of four objects that each have the mass m, which means each of these have the same mass. So one is a large uniform solid sphere, one is a spherical shell, we have a small solid sphere, and a small uniform shell. Okay, so we have all these objects, and for each of them the particle is the same distance away. Okay, and each of them has mass m. Well, when we find the gravitational force on something, only two things matter. Well, three things, but two things matter about the one object. How much mass it has, and how far away it is. Okay, for each of these, they have the same mass, okay, and we're at the same distance from their center. Okay, which means that for all four of these objects, we experience the same gravitational pull. Okay, and so the answer here is that they are all the same because for each of them you're the same distance away and they have the same mass. Okay, the key here is that you are outside the four objects because things change once we start to get inside of them. Alright, so I'm going to make a plot that shows the relationship between the gravitational force and the distance you are away from something's center. Okay, so force versus radius. Now, a radius of 0 means that you'd be inside the object. So let's say that this is the planet Earth, and we'll just draw it on our graph so we can kind of get a visual here. Okay, so this is the planet Earth, and this is its center. If you're at the very center of the Earth, there's actually 0 gravitational pull. We'll get to that in a second. So we're going to focus on what happens when you're outside the planet Earth. Okay, gravity is strongest when you get to the surface of the Earth, and as you go away, it decreases as 1 over r squared. Okay, it looks something like this. It will never reach 0, always going to approach 0. Okay, if we got to infinity, right, if r was equal to infinity, then there would be no gravitational force because r would be so big you're dividing by infinity, you get essentially 0. But other than that, you can't really escape the gravitational pull of the Earth, or of anything for that matter. This graph looks the same for any object, it's just the value for f would be smaller or bigger. Okay, now the tricky part is what happens if you start to go inside the surface of the Earth. Because let's say that you've gone in, you're creating a tunnel to the center, so let's say you've gone in just a little bit. What happens is this. You're only accounting for the mass that's basically inside of your location. Okay, all the masses out here, their gravitational pull on the person that's dug this hole, they all balance out, they all cancel out, they all add to be 0. And so now we only account for the gravitational pull of the amount of mass that's in here. Okay, and at the same time, the radius has decreased. Okay, and so that you're dividing by a smaller r squared. And the effect that has is to have it be decreasing in a linear fashion until you get to the center of the Earth, where if you ever made it to the very center of the Earth, you would feel 0 gravitational pull from the Earth. Okay, because all the pull from all the mass all around you would be kind of canceling out. So if you were to graph the gravitational force of the Earth, outside the Earth it looks like that, inside the Earth it looks like this. Okay, now kind of the assumption we're making is that the Earth has a uniform density. It doesn't, but we're going to assume it approximately does. Now let me show you another kind of planet. Okay, this is a very strange kind of planet that's never been discovered yet. Okay, with all of its mass located on the outside. So this planet is a shell. Okay, well, if you're standing on the surface of the shell, then you're going to experience the same amount of force as if you're standing on the surface of the Earth. Okay, but what's going to happen now is that as soon as you go inside the shell, now all these masses are canceling each other out, okay, and there's no gravitational force inside, and so it just goes from this peak. The second you get inside, it just drops straight to zero for the rest of the time. And this is for any kind of shell where you're inside all the mass is outside of you. So, like, I don't know if you've seen, I've never really played played video games, but there's the one Halo from when I was in high school, and they would like go onto this ring world. There's just this big ring. If you're standing inside of a ring like this, you would feel no gravitational pull from the mass because all of it would be canceling out. And so in a case like this, if you wanted to create gravity, you'd have to cause it to rotate, and that's a different conversation. But for the gravitational pull from each chunk of mass, it would be equal to zero. Okay? Okay, I want to do one more example here. So if the Earth were to collapse in on itself and turn into a black hole, let's look at how this might change. So if a black hole that has the same mass as the Earth, okay, but it's shrunk to this tiny little size. Well, let's start here for the position that would be equivalent to the Earth's radius. So as you're approaching this black hole, gravity from the Earth and gravity from the black hole are approximately the same. You wouldn't be able to tell the difference. Okay? But here's where the difference comes up. As you get closer, okay, no longer is the amount of mass decreasing and the radius is decreasing. So once you get to this point, this is where things change. If you are the same distance from this black hole as you were from when you're standing on the surface of the Earth from the Earth's center, then nothing would be different. But as you get inside, now this is going to increase. Okay? So that's why the black hole is really strong when you get really, really close to it, but when you're a large distance away, it would feel the same as if it hadn't turned into a black hole at all.